Hello, my name is Robert Smith, and I'm with New River Community College. And today we're looking at the effect of buffer system and how when you add acid or base to the buffer system, how it changes the pH. It's the whole point of a buffer system is that it keeps the pH relatively constant or very close to constant. Um, so when we are looking at this particular example, we are looking at nitrous acid and sodium nitrite as the buffer system. And then we're going to add zero point 0.1 moles of hydrobromic acid to 1 liter of the buffer solution. So really what we want to look at is our concentrations. This one is relatively easy, but if you were to be in an exam or a quiz, this volume might be different. It might be 4 liters or it might be half a liter, and you'll want to make sure you calculate the concentration based on that. So let's get started. There's going to be several ice tables involved, so just be prepared for that. So first, let's look at the buffer system, and we'll calculate the pH of this buffer system. And what we need to think about is how, so for our sodium nitrite, it's going to go from NaNO2, and it's going to be a one-way reaction to sodium ions plus nitrite ions. So whatever concentration we had initially of sodium nitrite, as soon as it hits solution, we now have that same concentration of sodium ions and of nitrite ions. So our initial concentration of nitrite in this solution, in this buffered system, will be 1.0 molar. So we're going to start our ice table by signifying that we're dealing in molar, and then we're going to focus on the acid. So nitrous acid, O2, is a weak acid, so it'll be in equilibrium with protons plus nitrite ions. And we know that we're starting off with 1.0 molar of nitrous acid. And because of this dissociation that we listed up here, we're also going to have that same amount of nitrite ions. But we start off with no protons. So this is our I, our initial. Then we want the change and the equilibrium. So for the change, we don't know what that is. So we're going to use X. And as the concentration of nitrous acid decreases, the concentration of both protons and nitrite ions will increase by that same amount. So they should have a plus X to all terms. So at equilibrium, we have 1.0 minus X. And then for protons, we have X. And for nitrite ions, we have 1.0 plus X. And then when you look up your acid dissociation constant in your textbook or online, you find that it's approximately 4.5 times 10 to the minus 4 for the acid dissociation constant of nitrous acid. And then that's going to equal the products over reactants, very similar to all the ice tables we've done before. So products would be X times the equilibrium value for nitrite ions, so 1.0 plus X, all over our reactants, which would be 1.0 minus X. But because 4.5 times 10 to the minus 4 is so small, we can also, we're going to do an approximal method wherein we're going to say that X is going to be small enough that adding it or subtracting it from 1 molar is not going to change the concentration by any significant amount. So we're going to use the approximation, and that makes it so that it's X times 1.0 over 1.0. So that means that X is equal to 4.5 times 10 to the minus 4. And that is also equal to the number of protons that we have, so, or the concentration of protons that we have. So then we can calculate the pH of this buffered system by saying negative log of the concentration of the protons, which would be 4.5 times 10 to the minus 4. And I should probably denote that that's molar. This is also molar, but we don't include the unit because it's based on the standard state of 1 molar. So, and this will give us a pH of 3.45. If you can hear my dog drinking water in the background, I apologize. So our buffered solution is 3.45, has a pH of 3.45. Then we want to add our hydrobromic acid, and we're adding 0.1 molar of it because it's 0.10 moles and 1 liter. So moles per liter, that gives us 0.1 molar. And because it's a strong acid, HBr, will go to H plus Br minus. Bromide is a spectator ion. We're only interested in the protons. So let me switch because we're doing a different thing now. So now I'm blue, and so we're going to start with a neutralization of the excess protons. So we're going to start with nitrite, O2 minus, plus H plus will bring us to HNO2. This is an equilibrium, but we're interested in neutralizing it, so we're using the nitrite ions to overcome the to complex with the protons. So we start off with because it's 1 liter, we start off with 1.0 molar of nitrite ions, and the same with nitrous acid. And we also know that we're starting off with 0.10 molar of protons because of the dissociation of the hydrobromic acid here. And so we know that we want it to completely neutralize, so we're going to subtract 0.10 molar from our protons. This is also an ICE table. And we're going to do the same with the nitrites. And we're going to add 0.10 to our nitrous acid. So we end up with 0.90 for nitrite ions, 0 for our protons, which is what we wanted. So that's good. And then 1.1 molar for our nitrous acid. So, and then to finish this off, what we do is we do the same thing that we did above, except now we have new values for our nitrite and our nitrous acid. So again, we do HNO2 is in equilibrium, and we're going to do it as an ICE table, is in equilibrium with H plus NO2 minus. And initially we have 1.1, 0, and 0.9 because we've made sure that our protons started at 0 in this particular reaction. Okay, and now the change is going to be minus X for our nitrous acid and plus X for protons and for nitrite ions. So our equilibrium will be 1.1 minus X, X for protons, and 0.9 plus X for nitrite ions. So then we can do exactly like we did before. We can say that 4.5 times 10 to the minus 4 is equal to x times 0.9 plus x, but we're going to use the approximation method, so we're going to just say it's 0.9. And then at the bottom would be our reactants, 1.1 minus x, but again, we're using the approximation, so we're just going to put 1.1. And then this is going to make it so that x is equal to 5.5 times 10 to the minus 4 molar, which is also equal to the concentration of our protons. So to get the new pH, let's use a different color. pH is going to be equal to negative log of 5.5 times 10 to the minus 4, which is going to give us a pH of 3.26. So you can see adding about a tenth of the amount of hydrobromic acid only dropped the pH by about 0.19. It's very little drop for how much strong hydrobromic acid you've added to the solution. And that's the power of the buffering, the buffer system. So, and that's how you would deal with a problem of this nature. And you can pretty much guarantee you'll experience it at least once or twice in your time in this class.